In this tutorial, I'm going to show you how to graph all different kinds of rational functions. So before we do this, there's a few things that we need to know. Okay, so the first thing is that all rational functions are always in this form. F of x equals some function over another function. We've already looked at some simpler forms of this, but we're going to take a look at some more complicated versions of it and figure out where its asymptotes are and its zeros and all that good stuff. So the first thing that we're going to talk about are how to find the x-intercepts of all rational functions. So the first thing that we're going to look at are that the x-intercepts of rational functions are the real zeros of p of x. So before we can actually do anything with this, we have to understand what it's saying. What it means by real zeros versus anything else is that we're not looking for imaginary numbers. Zeros, remember that there's three other words for zeros. And they are solutions, roots, and x-intercepts. So all four of those words mean the same exact thing. The next thing that we have to make sure that we understand is what this p of x stands for. And if you look up here in white, it says p of x over q of x. So what we're looking for the x-intercepts are the zeros of whatever is in the numerator. And yes, we will take a look at examples as to how to do this. In fact, we're going to do one right now. Okay, so let's take this example. We have y equals x plus 1 over x minus 2. Note that x's do not cancel because they're not an x in every single term. And just before we do this x-intercept, this might be a good time to review this. Please look at this fraction x plus 1 and x minus 2. Notice that this term has an x in it, this does not, this does, and this does not. You cannot eliminate any common factors unless every single term has that factor in common. And in this case, they all don't have an x, so we are not able to do this. So we're going to find out where the x-intercepts of this function are, and to do that, we are only going to look at the numerator. We're not even going to worry about the denominator when we do this. So I'm going to set x plus 1 equal to 0. That's how I'm going to determine my x-intercepts. And to solve this equation, I would minus 1 from both sides, and my x-intercept would be negative 1. So that's what it's talking about, the x-intercepts. So let's take a look at the second piece of information that rational functions can tell us. Okay, so the second thing that we're going to look at are the vertical asymptotes. And vertical asymptotes are at each real zero of q of x. Now let me bring in that previous function that we had and we can take a look at this. Okay, so our function was x plus 1 over x minus 2. And over here to the side, I just reminded us which part of the fraction means p of x and which part means q of x. So we are going to look at the denominator, and we are going to find the real zeros of it, which means that we are going to set it equal to 0. So I'm going to do that right down here. And to solve this equation, I'm going to add 2 to both sides. And that means that x equals 2 is one of my vertical asymptotes. So on a function, or on a graph I should say, at x equals 2, so that would be 1, 2 here, that is where my vertical asymptote is. Okay, that's all that means. There may be more than one. A lot of these problems that we're going to get into are going to have more than one, so just watch out for that. So the next thing that we're going to look at is about horizontal asymptotes. Okay, so this is where it kind of gets tricky. The horizontal asymptotes, unfortunately, are a little bit tricky to determine. We're going to take a look at some different examples of each kind of situation that you can look into. But before we do that, we have to make sure that we understand what degrees are when we talk about p of x and q of x. So let me write this in here for you real quick. So let's, for instance, take into consideration the problem that I just had up, x plus 1 over x minus 2. Both of these parts of my fraction have particular degrees, and the degrees is just the exponent, in fact the biggest exponent of any of your terms. So in the numerator, the exponent on my x is a 1, so the degree would be 1. In the denominator, I have the same exact thing. So what we're going to do is whatever the largest exponent in the numerator is we are going to denote that as m. Okay, whatever that may be. And then whatever is in the denominator, we're going to denote its exponent as an n. So the properties for horizontal asymptotes are all based around the comparison between m and n. So let me show you. So what if the degree in the numerator is less than the degree in the denominator? For example, I have x plus 1 over x squared minus 1. Okay, so that would be the difference. The numerator's biggest exponent is smaller than the largest exponent in the denominator. So if this is the case, your horizontal asymptote is automatically y equals 0. No ifs, ands, or buts about it, which kind of makes that easy. Now, the next situation is going to be if m and n are the same, just like in the problem that we were looking at, which once again was x plus 1 over x minus 2. So how do the horizontal asymptotes come out to be? And all you have to do is take a look at its coefficients. So notice that in front of the x in the numerator, there's a 1, and in the denominator, there's also a 1. So the way that I would determine its asymptote is I would divide those coefficients by each other. In this case, I would have 1 over 1, which means that my horizontal asymptote is y equals 1. So that was really simple. Let's take a look at one more. Let's say I have x plus 1 over 3x minus 2. Okay. Once again, the exponents are the same. They're both 1 and 1. But the coefficients is what's going to tell me where my horizontal asymptotes are. So the coefficient in my numerator is 1 for the x, and the coefficient of my x in the denominator is 3. Therefore, I'm going to do 1 over 3, which means my horizontal asymptote is y equals 1/3. Okay? Now the last situation is if m is greater than n. And the case with this is that there are no horizontal asymptotes if you have this case. So if I have, let's say, x squared over x plus 1, notice that this exponent is larger than the 1 exponent down here. Therefore, its horizontal asymptote would be y, not equals, but y does not exist. Or we can just say the horizontal asymptote does not exist. Okay, however that you want to say it is okay. So DNE is a common acronym for does not exist. And that will conclude this tutorial.